Hello everyone, my name is Mohammad Hanzil Akib Rashwan. Today I want to discuss with you about the task I have been given from data scientist for machine learning internship program. I have assigned to set B, which includes 4 different questions, and I want to discuss and share with you about the solutions I provided here. Now the first question is, outline an algorithm for finding an MST in a distributed system. There is also a follow-up question which is, in real world machine learning scenario, would you use the MST? Now answer to the first part of this question. What is MST? MST stands for minimum spanning tree, which is to connect all the points or nodes with the least total cost without forming any loop. Now, as we all know that in a distributed system, each node only knows about its direct neighbors and their edges or like weights. So, to find the MST for a distributed system, I would like to use the GSS algorithm, which is founded by 3 individuals, Gallagher, Hamlet, and Spira. Now, in this algorithm, first of all, each node considers itself as a separate tree. Then each node tries to find their minimum outgoing edges. Then the nodes communicate through messages to agree on merging their components through the smallest edge. Then two components connected by the smallest edge merge into one bigger component. This process repeats or continues until all the nodes are the part of a single connected component or the single MST. Now, answer to the following question, I would like to use MST in real world machine learning scenarios because I can use MST for sensor network clustering, for feature selections or dimensionality reduction, which is very important in machine learning, and I can use it for graph based clustering. Now moving to the next question, which stated that given a large stream of user interaction, design a data structure in order of log n time complexity for range sum queries and updates, which supporting both exact and approximate aggregation for downstreaming feature generators. There is a follow-up question also, which is, how would you parallelize updates for distributed feature stores? Well, we all know that Fenwick tree and segment tree performs order of log n time complexity to range sum queries and updates, but there is also a fundamental question that supporting both exact and approximate aggregation. Now we all know that between Fenwick tree and segment tree performs better for aggregation, like different types of aggregation. So I choose segment tree and I designed it as a hybrid segment tree for exact and approximate aggregation. Now to design that hybrid segment tree, I have to classify the classes here. In node class, I have 3 components like exact sum of for the range, number of elements, and approximate sketches. Then the segment classes here. Now, in order to perform the update operation in order of log n, I have find out the purposes first here. My purpose is to update a single element's value and reflect the change in all relevant tree nodes. So I have used recursively this update function here to navigate down to the target leaves and then update that and then recalculate the parents node sum. Here exact sum and counts are used to track the total values and the number of updates which supports both exact and approximate aggregation. Now let's move on the query operation here, which is also performed in order of log n time complexity. Now this function computes a range sum query in a segment tree. The range is from the left to right, here I indicated, and then I have also used this function recursively here because I need to traverse the tree segments and is giving non-overlapping parts. overlapping parts. Now the answer to the follow-up question, that how to parallelize, or it's stated that how would you parallelize the updates for distributed feature stores. Okay, now I can parallelize here by sort them by range or keys, which is like each machine can handle one range, and then each shard maintains its own hybrid segment tree, and I will periodically merge to the roots, like where we find the exact sum, then it will be added directly, and if we find the like approximate sum, then sketches are merged, like count, min, sketch, and others. Now moving on to the third question, which is you are asked to designing a machine learning model catches, explain how a split tree helps to optimize access patterns and what that are the trade-offs with compared to LRU catches. There is also a follow-up question, which when would splaying harms the latency in serving prediction? Well, now the question is asked to design a machine learning model catch, but before that we need to concern about few important things about our catch. What our catch should do: it should retrace model fast, providing low latency. It should adapt automatically to access frequency and manage limited memories and handle concurrent requests safely. Now we need to, what is a split tree here? A split tree is a special kind of binary search tree which is self-adjusting, and it automatically moves frequently access item near to the roots, and by that it is provides like it makes them faster to reach. Now designing a split tree, I first of all I define different types of classes, like model class, where I hold a catch entry by key or model and left and right pointers. Then the split tree catch class, which manages catches with limited capacity using the splay for quick access. Now there I defined a function splay, which is to move the access node to the root, which means I can move the recently used node to the root and make it faster for the next access. Then here I also use the get and put functions here. I get to bring the model with the key to the root and return if it found, and put it to insert or update any model. I also provide the evict function in order to remove the least recently used access nodes here. Now moving to the next question of the question number 3 is that how a split tree helps to optimize access patterns and what are the trade-offs. I have discussed here about the trade-offs with the LRU, means least recently used catches, and the split tree, and I also discuss here about how it optimizes access patterns. Now there is also a follow-up question, that when split tree harms the latency. Well, if like our model, if heavily concurrent access happened here, then it will increase the latency, and if each model access with no repetition, then split tree adds extra rotation, which also uh, harms our latency. Now moving to the fourth question, which is build a system to support efficient merging and querying of connected users components in a social graph as edges are added or deleted for clustering machine learning. There's also a follow-up question here: how does the union by rank and path compression speed up large scale machine learning graph operation? Well, first of all, in order to build a system, I already used here the path compression and the like union by ranks operation to make it faster. Now what I have done here, my purpose is to update a single node's value and reflect the changes in all relevant nodes. Here I used the disjoint set function, or we all know it as DSU or Unified Data Structure. Now let's build the system design. What are the idea? The idea is here that each user is a node in the graph and each connection is an edge between two nodes, and we maintain this connection using the DSU structure. The DSU here performs two main major operations, which is find and union. Find means it finds the components like a user, which cluster or component a user belong to, and union means it merges the components of two connected users. I have used here, I've designed the DSU structure here and defining the find function here and union function here. I have already said that I have used the path compression and union by ranks here in order to make it faster. Now moving to the follow-up questions, like how does the union by rank and path compression which I used here speed up the large scale machine learning graph operations? Well, it speed up or optimizes our models for large number of users, like when you have millions of users, but it helps in different ways, and combining these two ways would be a massive optimization here. What path compression does here? Path compression does that when finding the root of a node, it flattens the tree structure by directly linking all the nodes to the roots. So next time when we finding the same user cluster is almost order of 1 per operation. And union by ranks helps us that when we merge two trees, always attach the smaller tree under the large one. It prevents the tree from becoming tall. So if we combine both this technique, it will give nearly amortized time complexity, like order of alpha of n time complexity per operation, which is very near to order of 1 time complexity, means which is faster than even order of log n time complexity. This is that this is how I have built I have answered these questions here, and thank you everyone for having me.